Okay, so let's start our discussion today. Assalamualaikum warahmatullahi wabarakatuh and good morning to you all. Um, Before we move on, can you respond to me? Can you hear my voice?
Yes.
Okay, thank you. Because last week I got a meeting and everybody complains that uh, my voice is not loud enough. So hopefully I'm doing okay now. What we are going to do today, we will have a look at shell structure, not from theoretical point of view, but hold on, somebody try to get in. Uh, Shell structure, not from theoretical point of view, uh, but more on how we can do shell analysis in Ansys. So that's what we are going to do today. Before that, I would do quickly um, explain to you shell structure or shell element and how that element is different to the in-plane element. Last month on Monday, we have recording. So I send you the link to the video recording of membrane structure or in plane structure, and on that video I explain membrane in plane element in the form of triangular elements. So I hope that everybody here, every student, you have got a look at that recording files, and hopefully by now you have some idea, and you have also understand theoretical aspects of a membrane element. So hopefully you have seen that. And what we do today is not membrane. What we do today is simulation on shell structure. So that's what we will do today. All right. So by the way, your attendance link is on the chat section there. So if you go to the chat section, then you will find your attendance form, and the link is, I mean, the link for the attendance form, so which you can access, and please make sure that you fill in your attendance. Fine. And now I'm going to go to presentation mode, so that I'm going to review quickly on membrane and shell. Very quick.
Sir,
Yep.
you forget to record.
Okay, as usual. Hold on. So I need, okay, somebody try to get in. Okay, to record. So I'm doing recording now. Let's wait for a moment. All right, so now we are on record now. Okay, so now let's go to the slide here. All right, so can everybody see what we have here on the screen? I'm displaying shell and plate and membrane structure. Can you see that? Please respond to me, please.
Yes, doctor.
Fine. Okay, so this slide here is part of the video record that I sent you last month. So over here, we have a structure, and hold on, somebody try to get in again. I will admit that student. All right, so let's continue. If there is any technical glitch here, let's just make sure that you let me know. So this is another student try to get in. Um, okay, I will admit this student here. Fine. So let's have a look at this tree structure here. Uh, is there somebody trying to get in? Let me check again. Oh, yes. Okay, let's move on. We haven't started yet. Fine. I repeat again. We have three different this tree structure here, the one on the top left, top right, and the one on the bottom left here, they look the same, but actually they are not. So let me see if I can demonstrate that to you. All right. So can you see me holding this? Can you respond to that?
Yes. Yes.
Okay.
Yes.
Probably it is small, but yeah, you still can see me holding this board here. So this is a flat structure, all right? Flat structure. That's the support. That's the support. So the structure here on the left, top left, please observe the load. The load is, and I hope you can see that, the load number one is here, number two is here, and the load number three is here, okay? They have the same condition, or they have the same situation of load actually, that all of this load, they are in the same plane of this structure. All right, the same plane, same plane, the same plane, the same plane of this, meaning that this is not in the same plane, this is out of plane. So if the loading is in the same plane of this structure, this flat plane structure, then we call it in plane structure, in plane or membrane. Now, let's move on. If we go to this structure here, the structure, the loading is, the first load is something like that. That's the second load. And the third load. You can also see bending. Look at the way I do the bending. Okay, look at the way I do the bending. So that is another type of structure. We call it plate structure. Okay, plate structure. And now let's move on to the structure at the bottom left here. If you look at the loads that are working on this structure, the bottom left, number one, you have this in plane load. In plane load, okay, but also you have out of plane. So, and also you can see that we have bending on this cell structure. What are those? Those are different, okay, I'm talking about what are those structures. This one here is in plane structure. Over here we have plate structure. When the loading is out of plane and you got a bending. And over here, the loading is in the same plane. If what's the difference between the load, sorry, what's the difference between the behavior of this structure and that structure? The behavior is over here, you don't have bending moment and you don't have shear force. Over here, because you see that the load is out of plane, of course, there will be bending. Just remember what you learn when you talk about beam and when we talk about bar. In bar, you don't have bending. But in beam, you have bending and also shear. So in membrane problem, you don't have bending. You have only in plane loading. Then all the stresses are because of in plane loading. And when you talk about plate, our structure on the right, the plate, then we have bending, we have shear, meaning that the stresses there will also caused by bending and shear. The stress on the structure on the left is not. The structure on the right, yes, due to shear force and bending. And the structure at the bottom here is combination of both. The structure at the bottom is suffering because of in-plane loading, because of shear, and also because of bending. All right, so I hope you see the difference between membrane, between plate and shell. When we talk about membrane, then of course you are going to make use membrane element. When we talk about plate, then you are going to use plate element. And if we are working with shell structure, then you have to make use shell element. All right, so that is the difference between membrane, plate, and shell. So if I'm asking you during the test, we'll have the next exam, you have your test 2 later. I might ask you the behavior and the difference between a membrane, plate, and shell. Just like I'm asking you, for example, the difference between truss and beam and bar. So on the right here at the bottom is a representation of shell behavior, which if you look at what we have here, shell is a three-dimensional actually, and it will be able to deal with a force that is perpendicular to the element, force that are in plane, as what you see here, and also bending. So that is the behavior of shell element. I'm not going to talk in detail about the theory of shell, If you want, you can find that in the literature. But if you look at the recording that I have shared with you last month, then you will find the theoretical approach on finite element analysis on membrane in the form of a constant strain triangle element. So I'm not going to go into detail to shell, and I'm so not going to go into detail to plate, but sufficient to for you to understand the concept and the difference between these three type of elements. I think somebody just now tried to join. Okay, so that is our discussion just now on the concept, not so much on the theory, but on the concept and the behavior of a membrane, excuse me, membrane, plate, and shell elements. What we are going to discuss today is shell structure, and I'm going to explain to you what we are going to do uh, in Ansys, and also the structure, the shell structure itself that we are going to have a look at today. Okay, so I'm going to go to our structure that we are going to do the modeling and analysis today. Okay, so can you see what we have here on the screen? Can you respond to me that, please? We have a box type of structure.
Yes, Prof.
Yes, Prof.
All right, nice. So this is what we are going to simulate today. We have, well, a box here. The dimension of the box is, you have the 3000 millimeter length, 3 meters length. The height is 500 millimeter, and the width of the box is 1000 millimeter. So this is a kind of cantilever, actually. This is a kind of beam, but the beam now is instead of made of a solid beam, what we have here is a hollow beam. So the box in this case, of course, a box in this case is hollow, and that is our cantilever. So the beam in this case is a hollow structure. And the load is at the tip of the box. The load is at the tip of the box. We have 1000 Newton over here, and then 100 Newton and 80 Newton. Okay, so when we do our simulation, of course, we can change the magnitude of the forces. We can have 2000 over here, for example, and we can change that to 500 Newton or 80 Newton. Okay, so that's what we will do. Okay, fine. What I forgot to mention here is the thickness. So the thickness is, let's say the thickness is 1 millimeter all over. So we have a uniform thickness of 1 millimeter. The material here is steel. If you look at this data here, then this is going to be a mild steel, a ductile steel material. The modulus of elasticity, or we can call it Young's modulus, is 200,000 megapascal. You have the Poisson ratio there, which is 0.33. And this 250 megapascal is the yield strength. So later on, you can compare the difference. So you can compare the how close or how far is the maximum stress to this material strength that we have here. Okay, so that's what we are going to do in our structure here. Modeling using shell. So that's the first thing that we have to do. Next, we are going to. I think you can visualize. All right, you can try to visualize the structure here. So actually, the structure is simply just a kind of hollow structure like this. Not this is a kind of circular, but of course in this case the structure is a box, right? I hope you can see what I'm holding here. So it is a kind of box structure similar to this. We got a hollow here, and the support is somewhere over here. All right. So it's look kind of flimsy and thin. Looks thin and flimsy. Excuse me, I need to do something here. I somehow splash the water and sorry for the interruption. Okay, so you might think that this type of structure is flimsy. Flimsy means not strong, okay, and weak. So next we are going to reinforce that box with stiffener. We call it stiffener. So at the corner of this box, yeah, we are going to attach a stiffener. Stiffener is a kind of beam, slender beam. So over here, the stiffener is going to be having a cross section of 20 by 20 millimeter. Okay, 20 by 20 millimeter, which I'm going to attach uh, at this position. So hopefully by this, then this structure is going to be stiffer, more stiff. What is the application of this structure, this kind of structure, when you have the skin? See, we got a skin of 1 millimeter thickness, reinforced with this frame or stiffener. A lot. Practically, most of our vehicle is based on this. If you look at our car, for example, then you will find that the structure of the car or ship or airplane is actually made of a thin plate or thin skin or thin plane. And then at certain point, those skins or those panel are reinforced with beams. So basically, that's what you are going to do. That's basically what you have, sorry. And what you are going to do later when you do your assignment. In your assignment, I am going to ask you to do analysis on Stephen shell or Stephen panel, so that you are familiar on doing modeling and analysis of Stephen panel. Okay. In fact, what you see here is a very simplification model of airplane wing. Actually, basically, it looks like that. The main structure, not exactly, but yeah, that's the basis of aircraft structure. In this case, wing structure. which is a thin skin reinforced with frames. So that's, you can imagine that in that way. Excuse me. And you will find a lot of application of this type of structure. All right. So what we are going to do now is we are going to do the modeling of this structure using Ansys. The way we are going to do it in Ansys is we are going to create the geometry first. Okay, we are going to create the geometry first, and the way we do the geometry is we are going to have first points. What we are going to do is we are going to create points first, and we are going to create 8 points at the corner, at each corner of this box, meaning over here, there, over there, and etc. Over there and over there, and that means we are going to have 8. We are going to have 8 points. Next, we are going to create area. We are going to create surface from those points. So from the points here, 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 and there, we are going to create this surface. And from the point here, 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 and there, we are going to create this side surface on the right. Okay, so that's what we are going to do. And then once we have a complete box surface, remember we have collection of surface, not a volume, but a surface. Then we are going to create finite element model by doing automatic meshing, controlled meshing on those geometries. So that's what we are going to do. All right, so now let's go to Ansys. Remember that we have all these dimensions, 3000, 500, 1000, okay? So we are going to create our geometry first using Ansys. Fine, so now we are in Ansys. So can everybody respond that yes, you can see Ansys window on the screen? Can you respond to that, please?
Yes.
And of course, you see me drinking. Okay. We get another 5 to 10 minutes, and then we are going to have 15 minutes break before we go to the second session. As usual, you are going to go to preferences, structural. By now, you should be very okay with your Ansys, so I can do this quickly. Let's go to pre-processing, and we are going to decide, we are going to select element type, and in this case we will do shell. That's why I'm clicking shell here, and it is 3-dimensional shell, and the shell consists of 4 nodes. So that's what we will have here. Okay, so element type number 1 is going to be shell. And material now. Material model. Okay, it is structural, linear, elastic, isotropic, because we can also do orthotropic. Modulus of elasticity is 200,000 Newton per millimeter square. Newton per millimeter square, which is megapascal, of course. And 0.33 for our Poisson ratio. Nice. So now we have material 1, material number 1, which is steel. What we do now is we are going to assign thickness. We are going to assign thickness to our element. Okay. So for that, we go to sections. Normally, what you have done so far is you work with section when you want to create the cross section of the beam. Now we are going to assign thickness to our element. You go to shell, of course, lay up. Why the term lay up? The term lay up simply is because you can also do composite modeling. And when you do composite, then for every composite panel, you can have different layer. You can have different ply or lamina. Then we call that layup. So in this case, of course, we don't have layup because we are working with isotropic material. And let's give it a name. The name is going to be panel. Any name. And then for this section here, the name is panel. The ID is number 1. So meaning that you can assign any other property for your element, like thickness or cross section, with ID 1, because ID number 1 has been taken by this assignment. And the thickness is 1 millimeter. And automatically you have your material ID here, the material that we have defined before. So I click OK now. Hopefully everything is there. The thickness is 1. The unit is millimeter, the same unit as your geometry. I click OK. Right, so by now we have our element, we have the properties of the element, and we have also the material. So what we are going to do next is we are going to create points. So I will go to modeling, and I want to create key points in our coordinate systems. All right, so remember that that is the dimension. Okay, so I'm going to create point at each corner of this, and I will decide that this will be the origin. So the XYZ coordinate origin is going to be there. This here is x-axis, going up is y-axis, and to the left is z-axis. That's what we will do. Okay, so hold on. Point number 1 is going to be there. I click apply. Point number 2 will be, hold on, where is going to be? So 1 is 0, 0, 0. Point 2 is going to be 0, 1, 2, 3, 4. 1,000. 0, 0. Okay, I click apply. If there is any mistake, then of course we can make it right later. Point 3 is going to be 0, 500. Okay, I hope you can see that on the screen. Point 1 is here, point 2, point 3, and point 4 is going to be here. 1,500. Nice. Okay, so 1, 2, 3, 4. That will be our first 4 points, and then the next 4 points. Let me go to isometric view. It's going to be easier. Okay, so 1, 2, 3, 4. Now the next point is going to be 0.5. 0.5 is going to be at 0, 0, but it is going to be 1000 here. Because the width of box is 1000. I click apply. You see here, that's 0.5. 0.6. That's 0.6. And then 0.7 will be 0, 500. Sorry, 0, 500, 1000. Yep, correct. Number 8 is going to be 3000 over here. So you see here that I'm doing point based on the coordinates with the origin must be defined first. All right. So this is, I'm going to click OK for point 8. Right. So now you have 1, 2, 3, 4, 5, 6, 7, 8. You have 8 points. Our job next is to create the surface or the area by connecting all these 4 points to become a surface. So the first surface that I'm going to create is the surface at the bottom of the box by connecting this point, that point, that point, and that point. Let's do that. So before that, I'm going to save it first. Save DB. So you go to area, arbitrary. I'm going to do arbitrary by connecting points through key points here. So now I will have this point, that point, this point, that point, and then I click apply. So that will be the bottom surface, the bottom area. Next, we are going to create the top surface. There is a point here, and also there, I click apply. That's the top surface. Now I'm going to create the surface at this side here by connecting this to that point, and to that point. Apply. Okay. And finally, the one at the back there is also a surface, an area that I need to create by connecting points. And I click OK. All right, so now what we have here is our box here. This is geometry. This is not finite element model. So I'm going to save it here. Save. So yeah, you can see this box from any angle you want. That this is side view. That would be a front view. That with top view. That will be a back view, if I may say so. Okay. You can also, if you want, you can rotate by doing dynamic model here. You click that one, and then right mouse button, you can drag, and then you can rotate, just like if you do it in CATIA or SolidWorks. Okay. And you can come back also, of course, to your isometric view or oblique view. So, all right, so let's keep with isometric view. Okay, so I'm going to stop now so that we can have a break. So now we have our geometry. What we are going to do next is we are going to do meshing. We are going to do meshing, but that is going to be for our next session. Okay, that's going to be for our next session. Excuse me. So 15 minutes break. So we are going to come back at 9:10 before 9:11. So we are going to start between around 9:10 before 9:11 for 15 minutes break. Okay. Okay, so we meet again. Let's continue with our discussion on shell structure. Okay, so we are still in recording mode. Now I'm going to go to presentation mode again. All right, just to refresh your what we have done so far. So this is what we are doing. We are working with box structure, okay? And later on we are going to do reinforcing this structure with additional stiffener at uh, this position as what you can see over here. So now let's go to Ansys again. All right, so now we are in Ansys. Please respond to me that you have Ansys here on the screen.
Yes, Prof.
All right, fine. So what we are going to do now, we are going to mesh this geometry. And for that, I will go to meshing. And we are going to make use mesh tool. That's what we have here on the right. So what my strategy here is that I'm going to control the way we do the meshing. So for example, that at this edge here, also that edge, this edge, and of course we have another one over there. We will have 4 elements. Okay, so meaning that we are going to divide this edge here so that we will have 4 elements. And for the vertical edge here, we will have only 1 element. Okay, only 1 element. So that's what we are going to do. So let's do that. And we do it by going to this size control, and then we set the line. So that's what we'll do, because we are going to control the way we mesh from the number of element on a line. So that's what we do. We set here, and it asks which line you want to control. Then I'm doing this. I select all these 4 lines. I click OK. Next, it asks, are we going to control it by based on element length or division of element? So we do this box here, number of elements division, which is 4. Okay, so I click OK. So meaning now that at every edge of lines that we select just now, we will have 4 elements. And then we do the same for the vertical, this edge, this line, this line, this edge. I want only 1 element. That's what the plan. Okay, so if we don't do that, then Ansys will do it automatically for you according to what Ansys thinks is appropriate. So now we do it based on what we want. So once we do it, then of course we are going to mesh the area. The shape is quad and then map. Map means that mapping, okay? So let's see if we can do it now. Now I click, where is, okay, we click mesh here. And then which area we want to mesh, pick all area. Okay, so that's what we have over there. So now indeed that at this edge, we have 4 elements. And the vertical edge, we have only 1 element. So that is a very simple model, okay? Very simple model. Of course, by now you realize that you can, of course, always make your meshing more refined, but that's not what we are going to do today. Okay, so now let's save it first. We have our element, finite element model, and then what we are going to do now, we are going to apply the load and the boundary condition support. So you go to loads and define loads, apply, structural. I want to create the support. So what I want to have here is that this corner, this corner, this corner, and that corner over there, they cannot move at all. So displacement on those nodes, because we have the node, of course, over here, this, here, here, and there. I click OK. All degree of freedom, meaning that it cannot move, it cannot rotate as well. 0 displacement. All right, so now we have our support over there. What we need to do now is we are going to create force. So if we look at our model here, then that is where the forces are. Let's do it. It is 1000 here. Okay, let's make it 200 and over here 50. So let's do that. Instead of 180, let's do it 250. So let's come back there. We are going to have force at the node, this node over here. Okay, and the direction is going up, which is Fy, and the value is 1000 Newton. You see here the small red arrow. Next, we are going to do that over there on nodes, that node. Okay, it is going to be in the z direction, Fz. The magnitude is 200 but negative. All right. And finally, that node over there, it is going to be Fz and positive 50. Like so. You see the small arrow. You can also hopefully able to observe the direction of this arrow. Remember, that's x-axis, y-axis, z-axis. By doing this, now we have our finite element model complete. We can save it. And let me close this first. So now what we need to do is we will solve this model. So we finish with post-processing, and now we go to the solution stage. Solution, solve our current case. I click OK. And then I will do close. Okay, so now we finish solving this problem, and we can go to post-processing, and we read the result so that the post-processing can do the further analysis to display the result. I read result first. We have only one first set of result. I have read it, so we can plot it, and then you can have a look at the deformation shape and compare with undeformed. So that's what we have. So because of this load, you can see the way the deformation is happening. Although it looks rather extreme and drastic, but actually the deformation is small, because if you look at the maximum deformation magnitude is only 6 millimeter, 6.2, 6.3 millimeter. Remember, the length is 3,000 millimeters, so 6 out of 3,000 is not much actually. So this is exaggeration, of course. It looks a kind of bending up and also twisting because of the applied load. Yeah, so don't assume that the structure fails because you see this kind of extreme deformation. It is not, because in terms of displacement, it is still not that large. So this is not a proportional deformation, meaning the magnitude is not proportional. So now let's look at the deformation, but contour deformation, and then we go to degree of freedom. I want to see the resultant, the result in the form of resultant of displacement in X, Y, and Z. So that's what you have over there. The maximum deformation is at that point. You can see mx written there. And so that's 6.25, 6.26 millimeter, okay, millimeter is at that point. And it is relatively small, relatively small. Now, what about the stress? What about the stress? Let's go to element solution. And the stress, we can have a look at the von Mises stress. So that is the stress element base. And the magnitude of the stress is, you can see it over here, 22.96, around 23 Newton per millimeter square, or 23 megapascal. What about the strength? The strength, let's go back here. That's the strength, 250 megapascal. So yeah, it's strong. Strong meaning that it will not fail because of yielding, because the stress, the maximum stress of this structure is much below than the yield strength. The stress maximum over there is only 23 megapascal. Yeah, so this is a quite a safe structure with a reasonable deformation. Okay, what about let's have a look at this at this perspective. Okay, you have a thin box, 1 millimeter thickness, made of steel. Okay, the length is 3 meter, the width is 1 meter, the height is half a meter. Okay, and then you apply a load 1,000 Newton over here. 1,000 Newton is around 100 kilogram. So you can imagine as if you are only 60 kilograms, 70 kilograms standing. You stand at the corner here, all right? Or you push at the corner here, 100 kilogram. So that's what's going on. And on top of that, you have another force here, 200 kilogram. Sorry, 200 Newton, which is around 20 kilogram. Okay, so 1,000 Newton over here, yeah, is close to 100 kilogram. and 200 Newton over here, that's close to 20 kilogram, and another 5 kilogram here. So you can imagine, yeah, the load is not low actually, 100 kilogram for something that probably looks thin and flimsy, but it is able to do the job. It is able to do the job. Now, as I mentioned just now, oh, by the way, I'm going to show you contour plot of also stress, but from nodal representation. So we go to stress and same pharmacist. So that is stress contour, but taken from nodal references. So the result is more or less the same, and that is the contour. You can have a look at the other side. Okay. Okay. So, yep, that is how it looks. All right, now let's reinforce this structure. Let's reinforce this structure by providing stiffener, just like what we have over here. Okay, and the cross section of that stiffener, which is a kind of beam actually, is 20 by 20 millimeter. So that's what we are going to do. So for that, I'm going to plot elements so that I can see our element. So what I'm going to do now, I'm going to do manually. Attach beam element over here, over here, over here, over here, over there, here, by connecting the nodes, because you see we have a node over here, 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 and there. Okay, so I can show you by doing numbering, node number on, and then I click OK. Right, so that's the node number. That's the node number. That's the node number. But I'm going to make it off. Okay. So now we are going to create first our element. So you go back to pre-processing, and then you need to create beam element type. We have a shell, so we add one more. And we go to beam over here, to node, beam, and then I click OK. So now we have in our Ansys created two types of element. Type 1 is shell, the one that we have used. Type 2 is beam, the one that we are going to use. I click close. And of course, you need to define the cross section. You go to sections. Just now we did shell, but now we are going to go to the beam. Common section. There is a warning here. You see ID1, but there is a warning that we cannot use ID1 because it has been used by shell. So make it ID2. And then the name stiffener, stiff. Well, you can define whatever you want over here, but let's have a simple one, 20 by 20. Okay, so we have defined it. I click OK. So now I have these properties. Now I'm going to create beam element. So I go to modeling and create. I'm going to create element. Number one, we need to make sure that we select a beam for the element that we want to create. And also we want to make sure that that beam element is having the cross section that we want, and also the material that we have. So you go to element attribute. So the element type number we want is the second one, beam. material, we have only one, so be it, still. And then for the section, we want to have number 2 for stiffener. I click OK. So that's our element attribute done. And then I'm going to create the element now by connecting the nodes. So auto numbered through nodes. So you can observe what I'm doing. I'm connecting from here to there. Apply. Also next. So I'm connecting the nodes, that node, and then I click apply. Also over here. All right. And then this side over there. I hope I do not make any mistake here. And also at the bottom, I need to rotate. I have to, okay. So what I'm going to do here, I think I'm going to make it last. So I'm going to create this. I think I better make it now. So I want to rotate. And then I will do that again. And then I'm going to go back to the original. So what I've done just now, I have finished creating beam element along this edge. Now I'm going to do it also for this side over there. I need to go the same procedure again through nodes. So from there to there, apply. Also, this is manual process. So we have to be a bit patient. And of course, you can only do this manual meshing if the structure is not too complicated. And then I'm going to do the same at the back there. So I need to rotate. All right. Okay, that's the last one. All right, so now go back to isometric view. And yeah, basically that's what we have done. So now by doing this, then we have provided stiffener. Let's look at the model in a more realistic way. We have seen this, you have seen this before. Okay, so that's what we have. So now, if you observe, then we have stiffening. We have stiffening this structure, all right? I can enlarge this. Right, so yeah, you see here, that is our stiffener. We have stiffening our structure. Okay, this type of structure is, as I mentioned before, is very useful, and I hope this will help you later in your final year project, for example, or probably in your career later on. If you are doing engineering, you are doing modeling, then hopefully this will be able to help you when you design a structure which is a combination of skin and stiffener. Like a lot of this type of structure, you have it in car, for example, ship, airplane, a lot of structure. All right, so now what we do here is we are going to solve this problem. Okay, so I'm going to save DB, save database first, and then go to solution. We solve it now. Hopefully everything is okay. Solution is done. Close. By the way, this type of structure here is even though it looks simple, if you do hand calculation, you might take 100 pages to solve this problem. If you do A4 size paper, you do handwriting, doing calculation, just like what you have done in your test. So I think this cannot be less than 100 pages to solve this problem. And you might make mistake. Okay, so that's why, for this reason, we go to finite element software. Excuse me. We go to computer. All right. So we have solved this problem. We got the result. We go to post-processing. We need to read the result first. We read the last one, the last run, okay, last set, and then let's plot it, deform shape, deform and undeformed. So that's what you see. That's what you see. The shape of the deformation remains the same because the loading is the same, right? So this is the same structure, only we reinforce it. What's the difference now? The difference is that now the maximum deformation is less than 1 millimeter, 0.62. So it is less than 1 millimeter. Previously, if I'm not mistaken, it's about what? I can't remember. Is it 6 millimeter? But much more than this. Previously, it is still not much deformation, but now it is even less, 0.6 only. So now our structure is very stiff due to that reinforcement, So meaning that for this type of structure, with a simple reinforcement, then you can make it stiff. Even 100 kilogram is not significant for this kind of structure, which is very thin. We can also plot it on contour base, degree of freedom solution, displacement vector sum. So you see here, that is where we have our maximum deformation, which is 0.6 millimeter, which is very small in relation to the length of this structure, which is 3000 millimeter. Okay, what about the stress? That's the stress. That's the stress. Now, the stress, maximum stress is around 10 megapascal, 10 Newton per millimeter square. See this red color here? And they are, I think, somewhere over here. Where is that? Let me try to find those. I think it has to be somewhere over there. That one. So now the maximum stress is actually on the stiffener. That stiffener close to the close to the stiffener close to the support, because we have the support over here, over here, over here, over here. And that is where it is going to have maximum stress. Only 10, only 10. Before we do reinforcement, the maximum stress, if I'm not mistaken, is 23 megapascal. Now it is 10 megapascal. So now meaning that your structure is much stronger, much stronger. And of course, as usual, you can always have a look at the result using list. So you will have table. For example, nodal solution, you can have a look at the displacement. For every node, we have 40 nodes, 40 nodes. And you can see the deformation, displacement in X, Y, and Z direction. You can also have a look at the element solution, stress, for example, von Mises stress. Then for every element, you will find your stress over here. Okay. All right. So with that, then we finish our lab session. So basically, at this point, okay, you have learned all type of elements that you need to do in this course. You begin with bar. I mean, using Ansys, of course, not a theory, but using Ansys. You have done bar, you have done truss, you have done frame, you have done solid, of course, and you have done a combination of frame and truss. Now we are looking at shell and also combination of shell and frame. So with that, then you have all the elements that you need to solve your engineering problem for structural static problem. Okay, next week we are going to look at vibration. Next week we are going to look at vibration, how finite element will do vibration. That's either next week or the week after that. Let's see how we do it. Okay, so with that here, then we finish our session. You have the recording for you to look at. Okay, so I'm going to stop the sharing session here and go back to Google Meet. All right, is there any question? Any question from you regarding what we have done just now? Okay, so I suppose there is no question. So, okay, nice. We have done a lot this semester regarding finite element modeling and analysis. We have used Ansys intensively for this, for you to learn your finite element, and yeah, I think you learn a lot and you can do a lot now when you have to do your finite element analysis. Hopefully this is going to help you in your final year project and also in your career after you graduate from your ITM, especially if you are working on the analysis and design of engineering system. Okay, I'm going to stop now. Please make sure that you you watch the video on this shell simulation. So I'm going to stop now. Don't forget to fill in your attendance link, and we are going to meet on Monday. We are going to finish on Monday the theory and example of membrane structure. That's what we are going to do on Monday. And next Wednesday, as usual, we are going to do more quizzes. I hope we can do it. Okay, I think that's it for today. Thank you very much. I'm going to close now. Assalamualaikum warahmatullahi wabarakatuh, and good morning to you all. Keep safe. Thank you very much.
Thank you, Prof.
Thank you, Prof.